This video is for ELEC 1510 Logic Design. This is Lecture 15, Part 1 on the D flip-flop. This video corresponds to textbook section 5.4. A D flip-flop is a large aggregate device created out of two D latches. The first D latch right here has an input coming from what's called a clock signal directly to the enable input, and then the D input to the flip-flop is the first input to that first D latch. I'm going to call the output of the first D latch Y, and it behaves the same way that a D latch does as described in the previous video. The behavior of Y is just given by the normal behavior of a D latch, as I described in the previous video. For the second latch, the input to the enable signal is clock prime. This clock signal goes through an inverter first, and the D, the data input to that latch, is Y, the output of the first D latch. Then Q, the output from the flip-flop, is equal to the output from that second D latch. Again, flip-flops are edge-triggered devices rather than latches being level-triggered devices. And so we're going to explore how that works in the next slide. So again, we've got the D flip-flop here constructed out of two D latches. Now let's fill in a truth table to see how the behavior works. D and clock can be any of these values. Clock can be 0 or 1, D can be 0 or 1. Clock normally will alternate, but it can take, either of the values, 0 or 1. For the enable signal into the Y latch, that's this latch here, that is just equal to the clock signal, so it follows the clock 0, 1, 0, 1. For the enable signal into the Q latch, that's this latch here, that is the complemented version of the clock signal, so it's 1, 0, 1, 0. So then when clock is 0, the enable signal into the Y latch is 0, and that means that Y remembers its previous state. It doesn't change. So I'm going to call that state Y old. That means that Y is equal to what Y used to be. So for two rows in the truth table, Y is equal to its old state. When clock is a 1, that means that the enable signal into the Y latch is a 1. That means that Y is equal to D, which in this case is 0, and in this case is 1. Okay, so now in the first case, when clock is 0, that means that the enable input into the Q latch is a 1, which means that Q is equal to the Y input, which is Y old. For the other instance, when the Q enable line is a 1, Q is also equal to Y old because it's equal to whatever Y is at that time. When the enable Q line is 0, meaning that clock is a 1, Q remembers its previous state, which is Q old. So Q can only be one of two values, either the old state of Y, which is what D used to be, or Q old, which is what Q used to be. We're going to call Y old a new state. So that is when Y old is given by D. So that means that Y is remembering the data input, and that is being transferred into Q, and Q old is an old state. So Q only has two possible values that it can take, a new state or an old state. It transitions to a new state whenever the clock moves from 1 to 0. So then it goes from an old state to a new state. Whenever the clock transitions from a 0 to a 1, Y starts taking in new data, but Q just remembers its old state. Let's analyze the behavior of a D flip-flop internally as a function of a changing clock signal. This clock signal alternates between levels 0 and 1. And I'm going to go ahead and label each change in time as being a new time instance. So this 1 is time instance 0. The next following 0 is time instance 1, then 2, 3, 4, 5, 6, 7, and so forth. At time instance 0, the clock signal is at level 1, which means that the enable input into the Y latch is a 1, meaning that Y is just equal to D, and I'm going to say that Y is equal to D at time 0. Now at time instance 1, when the clock signal shifts down to a level of 0, that means that the enable input into the Y latch is a 0, and that means that Y holds on to its previous value, which means that Y is equal to D0. So it's not equal to D at time equals 1. D could have changed or not changed, but Y stores the value of D0. So when the clock signal has a level 0, that means that the enable input into the Q latch is a 1, meaning that Q follows Y. So Q is equal to Y, which at this time is equal to D0. It's not going to change at all, even if D changes. Now at time instance 2, Y now goes back to following D, so Y is equal to D2, but Q is going to remember its previous state, so Q is going to be equal to D0. Now again, at time instance 3, when the clock level shifts back down to 0, Y is going to remember its previous value, D2. Q is going to be equal to D2. And at time instance 4, now Y is equal to a new value, D4. Q is going to remain equal to D2, and so on. So you can see that Q gets a new value at every falling edge, and it remembers the value that it was at the previous time instance. So at time 3, Q is equal to D2. At time 5, Q would be equal to D4. At time 7, Q would be updated to be equal to D6, and so on. The type of flip-flop here that we've been talking about is a falling edge triggered flip-flop. That means that D changes values whenever the clock signal moves from 1 to 0. A negative edge triggered flip-flop has this symbol. You can tell a flip-flop as opposed to a latch by the fact that the clock input here has a little triangle next to it, as opposed to the latch, which doesn't have anything next to it. The negative edge or falling edge triggered flip-flop has this little circle next to it, indicating an inverter. The characteristic table for the negative edge triggered D flip-flop is that Q of t plus 1, meaning Q of the next time instance, is equal to the data point of the previous instance, D of t. The time instance is said to change at every negative edge. A positive edge triggered flip-flop has the exact same behavior, it just changes on a rising edge rather than a falling edge, and it's missing the circle at the clock input to the symbol. So Q of t plus 1 is still equal to D of t, meaning that the Q output stores the previous data that was entered into the flip-flop.